Hi, this is Brandon Rohr with How Decision Trees Work. Decision trees are one of my favorite models. They're simple and they're powerful. In fact, most high-performing Kaggle entries are a combination of XGBoost, which is a variant of decision tree, and some very clever feature engineering. The concept behind decision trees is refreshingly straightforward. Imagine creating a data set by recording the time you left your house and noting whether you arrived at work on time. Looking at it, you can see that for the most part, departure times before 8:15 result in punctuality, and departure times after 8:15 result in tardiness. You can summarize this pattern in a decision tree. The very first branching point is the question, did departure occur before 8:15? There are two branches, a yes and a no. For consistency, we'll keep all of our yeses on the left. Placing this decision boundary divides the data up into two groups. And although there are some stragglers and exceptions, the overall pattern is captured by placing this decision boundary at 8:15. If you depart before 8:15, you can be reasonably sure of getting to work on time. And if you depart after 8:15, you can be reasonably sure of being late. This is the simplest decision tree possible, a single branch. We can refine our estimate of punctuality by subdividing both the before 8:15 and the after 8:15 branches. If we add additional decision boundaries at 8 o'clock and 8:30, then we can divide up our arrival estimate more fully. Those before 8 o'clock are confidently on time. Those between 8 and 8:15 are probably on time, but not guaranteed to be so. Similarly, departure times after 8:15 can be divided into those after 8:30, which are almost certainly late, and those before 8:30, which still have a small chance of being on time. This decision tree has two levels. Decision trees can have as many levels as you want. Most often, each decision point or node has only two branches. This example has a single predictor variable and a categorical target variable. The predictor variable is our departure time, and our target variable is our punctuality, whether or not we're late. Because it has only two distinct values, it's categorical. Decision trees with categorical targets are also called classification trees. We can extend this example to the case where there are two predictor variables. Consider both the departure time and the day of the week. We'll start counting at Monday equals 1, so Saturday equals 6 and Sunday equals 7. Inspecting the data, we can see that on Saturday and Sunday, the green filled donuts, representing being late, extend further to the left. This means that leaving at 8:10 is probably sufficient to get you to work on time on a weekday, but probably not on the weekend. To represent this in a decision tree, we can start as we did before by putting a decision boundary at 8:15. Any departure times after 8:15 are likely to be late. Departure times before 8:15 are inconsistent. Before, we assumed that they would be on time, but now we can see in the data that that's not entirely true. To make our estimate better for the weekends, we can subdivide the before 8:15 departure times into weekday and weekend. Now, a weekday departure before 8:15 is confidently on time. However, weekend departures before 8:15 are mostly on time, but not entirely. We have updated the decision tree with a node that reflects this new decision boundary. Now we can further refine our estimate by subdividing our weekend pre-8:15 departure times into before and after 8 o'clock. Before 8 o'clock, almost all of the arrivals are on time, and between 8 and 8:15, the majority of them are late. Now we have our two-dimensional decision tree neatly divided into four regions. 2 of them reflect on-time arrivals, and 2 of them show late arrivals. This is a 3-level decision tree now. Note that not all of the branches need to extend down to the same number of levels. Now we can look at an example with a continuous target variable rather than a categorical one. When a model is used to make predictions about continuous numerical variables, it's also called a regression tree. So far we have looked at 1- and 2-dimensional classification trees. Now we'll look at regression trees. Let's consider the question of what time someone wakes up, as predicted by their age. The root of our regression tree is an estimate for the entire data set. In this case, if you had to make an estimate without knowing someone's age, a reasonable guess would be 625. This is the root of the decision tree. A reasonable first split is at age 25. On average, people younger than 25 wake up at 7:05, and people older than 25 wake up at 6 o'clock. There's still a lot of variation in the younger group, so we can split it again. Now the people younger than 12 can be estimated to wake up at 7:45, and people between 12 and 25 can be estimated to wake up at 6:40. The over 25 group can be meaningfully subdivided too. Those between 25 and 40 wake up on average at 6:10, and those between 40 and 70 wake up on average at 5:50. There's still a lot of variation in the youngest group, so we can further subdivide it. By slicing again on age 8, we can refine the estimates to more closely fit the data. We can also subdivide the 40 to 70 group on the 58-year line. Notice that we're getting to where we only have 1 or 2 data points per leaf of our tree. This is a dangerous condition and can lead to overfitting, which we'll talk more about in a minute. The resulting tree lets us make a numerical estimate depending on someone's age. If I need to estimate the wake-up time for a 36-year-old, for instance, I can start at the top of the tree. Are they younger than 25? No. Go to the right. Are they younger than 40? Yes. Go to the left. The estimate then becomes 6:10 a.m. The structure of the decision tree lets you sort people of any age into their respective bin and make an estimate about their wake-up time. We can also extend this regression tree example to have 2 predictor variables. If we consider not only someone's age, but the month of the year as well, then we can find even richer patterns. In North America, days are longer in summer months, and it gets lighter earlier in the morning. In this completely unrealistic example, children and teens are unburdened by the rigorous schedules of work and school and have their wake-up time driven by when the sun comes up. On the other hand, adults fall into more regular patterns, fluctuating only slightly with the seasons. Again, older people in this example tend to wake up a little earlier. We construct this decision tree much the same as the last one. We start with the root, a single estimate that roughly fits the entire data set, 630. Then we look for a good place to put a decision boundary. We split the data on age 35, creating 2 halves, one for our under 35 population with a wake-up time of 7:06, and one for our over 35 population with a wake-up time of 6:12. We repeat the process, subdividing our younger population on whether it is before or after the middle of September, and whether it is before or after the middle of March. This isolates the winter months from the summer months. Winter months have a wake-up time of 7:30 for those under 35, and in the summer months it's 6:56. Then we can revisit our over 35 population and split them again on age 48 to get a more accurate representation. We can also go back and subdivide our under 35 winter wake-up times on age 18. Someone under 18 in the winter will wake up at 7:54 as opposed to 6:48 for those over 18. You can start to see the emergence of the tall corner peaks. As we make each additional cut, the shape of our decision tree becomes a little bit closer to that of the original data. Also, you'll notice in the upper right-hand plot that the decision boundaries begin to slice the dataset into regions of approximately uniform color. The next cut continues this trend, focusing on dividing those younger than 35 in summer months to those older and younger than 13. The shape of the model becomes even more similar to that of the data. You can imagine continuing this process until the model closely represents the smooth trend underlying the data. Each decision region would become progressively smaller. The approximation to the underlying function in the data would become progressively better. The power of decision trees is not without pitfalls. An important one to watch out for is overfitting. Returning to our example of a single variable regression tree, age versus wake-up time, imagine that we continue to make cuts on the age axis until there were only 1 or 2 data points in each bucket. When we get to this point, the decision tree explains and fits the data very well. It fits too well. Not only does it capture the underlying trend, the smooth curve that the data follows, but it also catches the noise, the unmodeled variation that's included in the measured data. If we were to take this model and use it to make predictions about new data, the noise from the training data would actually make our predictions less accurate. Ideally, we want a decision tree to capture the underlying trend, but not to capture the noise. One way to safeguard against this is to make sure that there are more than a handful of data points in each leaf of our decision tree. That way, any noise will be able to average itself out. Another thing to watch out for is having lots of variables. We started with a one-dimensional regression tree, then included month data to create a two-dimensional regression tree. Decision trees don't care how many dimensions we have. We could, for instance, also add latitude, the amount of exercise someone gets on a given day, their body mass index, and any other variables that we think might be relevant. To visualize this, we'll use a trick shared by Geoffrey Hinton, a renowned deep neural network researcher. He recommends, to deal with hyperplanes in a 14-dimensional space, visualize a 3D space and say 14 to yourself very loudly. The challenge when working with many variables then becomes deciding which variable to branch on when growing our decision tree. If there are very many variables, then this can require a lot of computation. Also, the more variables we add, the more data we need to reliably choose between them. It's easy to get into a position where the number of data points is comparable to the number of variables. When our data set is represented as a table, this manifests itself as the number of rows being comparable to the number of columns. There are methods for dealing with this, such as randomly selecting a variable to divide on at each branch, but it's something to keep an eye out for and handle mindfully. As long as you keep your eyes open for places where decision trees might fail, you're free to take advantage of their strengths. Decision trees are fantastic for when you want to make as few assumptions about your data as possible. They're quite general. They can find nonlinear relationships between your predictor variables and your target variable, as well as nonlinear interactions between predictor variables. Quadratic, exponential, cyclical, and any other relationships can all be revealed as long as you have enough data to support all the necessary cuts. Decision trees can also find non-smooth behaviors, sudden jumps, and peaks that other models like linear regression or artificial neural networks can hide sometimes. There's a good reason that decision trees consistently outperform other methods on data-rich problems. Thanks for tuning in, and I hope this is helpful in building your next project.
Bayesian inference is a way to make guesses about what your data mean based on sometimes very little data. The way it works is tricky, but it's not magic. It's definitely something that you can wrap your head around, and it's not impossible to do so. My goal is that by the time we're done talking, you'll have a pretty crisp picture of how it works. Bayesian inference is just guessing in the style of Thomas Bayes, who was a nonconformist Presbyterian minister. He wrote a couple of books, one about religion and one about probability. So Bayesian inference is just guessing in the style of Bayes. So to illustrate it, imagine that you're at the movies and someone drops a ticket. You pick it up and you can see them from behind. You know they have long hair, but you don't know whether they're a man or a woman, so you have to make a guess. Based on what you know about the attendees at your movie theater, you might say, "Excuse me, ma'am, is this your ticket?" Now imagine instead that this person is standing in line for the men's restroom. Knowing this extra piece of information, you might make a different guess. Bayesian inference is a way to capture this common sense knowledge about the situation and help you to make better guesses. So to put numbers to this dilemma at the movie theater, let's assume out of 100 women at the movies, 50 have short hair, 50 have long, and out of 100 men at the movies, 96 have short hair and 4 have long. In this case, we can see that there are definitely more women with long hair than men with long hair. So it's a safe bet to assume this person's a woman. Now we just made a subtle assumption that there are about the same number of men and women at the movies. This assumption no longer holds when we move to the men's restroom line. Here, let's say there are 2 women out of every 100 people and 98 men, maybe women keeping their partners company. There's still one with short hair and one with long hair. It's still half and half long and short hair, but now there are 4 times as many men with long hair than women with long hair in this group. Now the safe money is to bet that this person is a man. So to draw this a little differently, out of 100 people at the movies overall, we'll make this assumption explicit that 50 of them are women, 50 of them are men, so this is how the different categories break down. In the line for the men's restroom then, they break down a little differently. So to translate this to math, the probability that a person is a woman is the total number of women divided by the total number of people, 50%. Similarly for men. Moving to the men's restroom line, the probability that someone is a woman is 2%, 98% for men. Now, Bayes' theorem is a little bit tricky, so to be very precise, we're going to have to talk math. So if you bear with me for just 3 probability concepts, we'll lay the foundation for presenting Bayes' theorem. The first one is conditional probabilities. If I know that a person is a woman, that's the condition, what's the probability that that person has long hair? So it's written as probability of long hair given that a person's a woman. So to get this, we just divide the number of women with long hair by the total number of women, 50%. And this doesn't change whether there's 50 women in your group or 2 women in the group. Still, if we know that a person is a woman, the probability that they have long hair is 50%. We can do the same thing with men. Probability that someone has long hair given that they're a man is 4%. So conditional probabilities, if I know that B is the case, what's the probability that A is also the case? This is not, you can't reverse B and A and have this be true. So for instance, if I know that the thing I'm holding is a puppy, what's the probability that it's cute? The probability is very high. If I know that the thing I'm holding is cute, what's the probability that it's a puppy? Well, it might be a puppy, it might be a kitten, it might be a hedgehog, it might be a small human. There's lots of things that it could be. So the probability there is less moderate. So these things are not interchangeable in conditional probabilities. Now, concept 2, joint probabilities. So what's the probability that a person is both a woman and has short hair? So to calculate a joint probability, you first find their conditional probability. Well, if I know that they're a woman, what's the probability that they have short hair? And then you multiply that by the probability that they're a woman. So in this case, 0.5 times 0.5, we get a 0.25, which is exactly what we knew it was going to be. And the same is true for all of our different conditions. So we can do this for the men's restroom too. The probability that someone is a man and has long hair, 4%. Someone is a woman and has long hair, 1%. Joint probabilities are different than conditional probabilities. Here, the probability that A and B is the case is the same that the probability that B and A is the case. So the probability that I'm having a jelly donut with my milk is the same as the probability that I'm having a milk with my jelly donut. These two conditions, these two situations are identical, so we can swap the order. And finally, concept 3, marginal probabilities. If I wanted to say figure out the probability that someone has long hair, I just add up all of the different ways that someone can have long hair. They can be a woman with long hair or a man with long hair. In the men's restroom line, that's a 1% probability plus a 4% probability, or a 5% probability overall. And you can do the same thing for short hair, 95%. Now, this last concept finishes our foundation. We can get to what we really care about. We know that this person has long hair. What's the probability that they are a man or a woman? This is a conditional probability, but it's the reverse of the one that we know. And we don't know how to answer this yet. So, this is where Thomas Bayes comes in. He noticed something really cool. You can calculate the joint probability that someone is a man and has long hair using the formula we saw before. And you can also calculate the joint probability that someone has long hair and is a man. Now, these are different formulas, but remember, joint probabilities don't care about the order. So these two things are equal, which means the stuff that they're equal to on the other side are also equal to each other. And we can do a little algebraic sleight of hand. And now we have a formula for what we want to know. If someone has long hair, what's the probability that they're a man? And we have this expression to the right. We can genericize that with A's and B's, and now we have Bayes' theorem, one of the top 10 most popular math tattoos of all time. So using this formula, we can go back to the movie theater and plug in what we know. We know that the probability that someone is a man. We know the probability that if they're a man, they have long hair. And we know the conditional probability, the marginal probability that someone has long hair, which is just the probability that someone's a woman with long hair plus the probability that someone's a man with long hair. And we plug all that in, and we can say if someone has long hair at the movie theaters, there is a 7% chance that they are a man. Similarly, 93% chance that they are a woman. Now, if they're in line for the men's restroom, because some of those probabilities change, that conditional probability changes. If someone's in line for the men's restroom and has long hair, there's an 80% chance that they are a man. And this is consistent with what we saw before. We know that there are 4 men and 1 woman for every 100 people in line for the men's restroom that have long hair. So 4 out of 5 long-haired people are men, 80%. It all adds up. So this example shows the mechanics of how to get Bayes' theorem and how it works. In practice, it's usually used a little differently. So to show this, we'll have to do a little bit of a detour and first talk about probability distributions. You could think of probability like a pot with just 1 cup of coffee in it. You can fill up, if you just have 1 cup to fill up, you can fill it all the way to the top. But if you have more than 1 cup, you have to share it around or distribute it. And you can share it in any proportion you want. So for instance, if we're representing the number of men and women at the movies, we could share it 50-50, but it'll always add up to 100%. We could even share it further into different categories. So here we see the joint probabilities of all of our 4 different categories that we were working with. And you can see that this is just another representation of the distribution representation that we were looking at before. Now usually when we look at this, they're side by side, probability instead of percentage, and shown in a histogram like this. It can be really helpful to think of these as beliefs. So for instance, if I flip a coin and hide the result from you, you might half believe it's heads and half believe it's tails until I tell you what it is. If I roll a die and hide the result from you, you might believe about 1/6 that it's a 1 or a 2 or a 3 or 4 or 5 or 6 until I show you the result. So these are what you believe. Probabilities can represent what you believe about something before you measure it. Similarly for Powerball tickets, and even for things that are more complicated, like let's say the height of adults in the United States in centimeters. You might believe that there's a very small chance that they'll be over 210 centimeters and a smallish chance that they're less than 150 centimeters, and then assign various amounts of this belief to all of the ranges in between. It still adds up to 1. It's like a bunch of cups of coffee lined up in a row, and you put a little bit in each one. The cups in the middle have more. And it shows how your belief about some individual is distributed before you've actually measured them. Now you can take these bins and chop them more and more finely, again and again, and if you keep doing this, you can get to something that's actually perfectly smooth. So it's as if you had an infinite number of very tiny cups and you put a tiny bit, infinitesimal amount of coffee in each one. At this point, it's probably no longer helpful to think of it in that terms, but just thinking of it as a continuous distribution, showing for all these heights, where am I placing my bets? What do I believe and how much? So once you have your beliefs, you can use it to answer questions about typical heights, the average, the median value, the most common value, or the mode. Now we'll use this in weighing my dog. I have a Shih Tzu named Reign of Terror. She's a little mischievous, and when we go to the veterinarian, Reign squirms on the scale. So every time we weigh her, we get a different weight. This last time we got 13.9 pounds, 17.5 pounds, and 14.1 pounds. What we want to know is how much Reign weighs. And this will be the basis for a decision. This is important. If her weight has gone up, her food intake will have to go down. And for her, this is a matter of life and death. So we don't want to make the wrong assumption and draw the wrong conclusion. So if you've ever taken a statistics class before, you know you can take these measurements, add them up, get the average, 15.2 pounds. You can calculate the standard deviation of these 3 measurements and also the standard error and come up with a 1.16 pound standard error, which when you show it graphically, this red curve now shows the belief that results from those 3 measurements, the distribution. The peak of that hill is at 15.2 pounds, and 1 standard deviation on that curve is our standard error of 1.2 pounds. So you can see looking at this that yes, it's most likely that she's 15.2 pounds, but there's a lot of that curve that sits outside of the range of 14 to 16. So yeah, she's probably between 14 and 16 pounds, most likely between 13 and 17 pounds, but she might even be lower than 12 and higher than 18. That is a really wide range, and it's not a great basis for making a decision. Now you can see the three measurements there, those three white vertical lines, and you can see why our belief is so dispersed, because those three measurements are pretty dispersed. It's hard to capture all that in one distribution.